I'm Dave Kassler, amateur radio call sign KE0OG, and welcome to episode 52. Can you use solar power for your ham station? Yes, absolutely. That's how I power mine. In fact, I even wrote an article about it in the April 1996 QST, only 21 years ago. I've still got that original Arco solar panel, though everything else in my system has changed. And I can still power my 100-watt SSB station on HF, plus all my VHF work. And I have enough capacity to run some extra lighting. My system has provided wonderfully stable power during that time. For quite a while, I didn't even own a utility-connected 12-volt power supply. I guess the first question to ask is if the sun is capable of providing the power. The Sun is an ordinary, mid-sized main sequence star about halfway through its life cycle. Don't worry, though, we have about 5 billion years to go before it retires. At its center, the Sun is a continuing nuclear furnace that converts hydrogen into helium. The outer part of the Sun glows from all the heat coming from its core. Because of the heat, the hydrogen and other elements in the outer part of the Sun are ions, and with all that heat, move a lot, and moving ions create very strong magnetic fields. The Sun is really quite a violent place. Fortunately, we're on the order of 93 million miles away from it. The temperature on the surface of the Sun is about 5,500 degrees Kelvin, and is a very hot object that emits light. By definition, we call this white light. Now, how much power can we capture from all those gazillion photons ramming the Earth's surface? The answer is quite a bit. The measure of how much power per square meter is called the solar insolation, and yes, that's a real word. And here's the fun part. All those photons hitting a square meter, a bit larger than a square yard, add up, are you ready, to a full kilowatt of power. Some is reflected back into space, but most of the solar visible light radiation is simply converted to heat. Is there a way to capture some of that? Absolutely. Many decades ago, scientists from AT&T, often called Ma Bell back in those days, were looking for a way to use the sun to power remote telephone repeaters. They used the photoelectric effect and invented the first photovoltaic cells. Although they weren't really very good at the time, well, over the past 60 or 70 years, lots of research has improved these to the point that when you buy the bigger panels, you can get them for about $1 a watt. Today's panels convert about 10 to 15% of light into electricity. That may sound low, but that means a meter square panel can produce 100 watts while doing nothing more than sitting out under the sun. That's all well and good, but there are a couple problems. First, the amount of sunlight varies throughout the day and goes to zero at night. We can solve the variability problem with batteries, but first we need to calculate how much power is needed for a typical station. Let's look at operating habits. Let's assume that you use a typical modern 100-watt single sideband HF rig every day for a couple hours. You listen more than you talk. Let's assume that you spend about half your time having QSOs. The other half is just tuning the bands. And when you're talking with your speech processor properly adjusted, you have a 40% duty cycle. Now, it's convenient when working with solar panels to work in amps rather than volts or even power. A modern HF rig with lots of internal electronics consumes about 2 amps during the time you're listening and a maximum of about 20 amps when you're transmitting. Okay, let's run the numbers. You're listening half the time, plus when the other station is transmitting, you're receiving half the time. So, out of the 2 hours you have your radio on, your receive-only duty cycle consumes 2 amps over 90 minutes, or 3 amp hours. Now, for the half hour you're transmitting, your duty cycle is 40%, so that's 40% of your 20 amps, or 8 amps, or taking time into account, 4 amp hours. So your total current usage per day is a mere 7 amp hours. Remember, we're talking current. Fundamentally, your solar panel has to chalk up a mere 7 amp hours to keep your radio humming all the time. Now, let's assume for the sake of calculation that you get 4 hours of sunlight a day. In that 4 hours, the panels need to generate 7 amp hours of current, or just 1.75 amp hours per hour, or more plainly, 1.75 amps. However, the sun doesn't shine every day, and there's less sunshine in the winter, so you'll want to have enough panels and enough storage capacity to give you an average of 7 amp hours per day over, say, a week. And what else do you need to power? How about a few lights and the charger for your handheld? You can keep adding things up. Just be sure that your panel is enough to cover all that averaged out over your week. If you apply this same logic to other loads, you'll find that you need quite a large array of panels, for example, to keep a refrigerator going. And running an electric heater is simply out of the question, just requires too much energy. Let's dive into solar panels another layer deeper. Fundamentally, each solar cell on the panel converts the incoming photons to moving electrons. An individual cell in full sunlight will generate a potential of 0.5 volt, and the amount of current is directly proportional to the area of the cell and the amount of sunlight. Now, as it turns out, these cells are current devices. They'll produce their maximum current at any voltage up to a limit. So if there are 0 volts across the cell, meaning it's shorted, it will continue to deliver the same amount of current. Let's pause on that for a moment. You can short a cell, and only the rated current will flow. You cannot burn up a solar panel by shorting it. In fact, you can measure the output of a solar panel by simply placing an ammeter across it, which short circuits this to give the so-called short circuit current. Now, let's dive a necessary step deeper. If you are charging a 12-volt battery, the panel is immediately operating at 12 volts. Let's suppose this is a 3-amp panel. The actual power delivered by the panel is 12 volts times 3 amps, or 36 watts. And it will push its rated current into the battery, charging it. But if you're charging a 6-volt battery, the system will operate at 6 volts and push its rated current. But in the 6-volt case, 6 times 3 is only 18 watts. The lesson here is that we want to run the panel at the point where the voltage times the current is the highest. This is called the maximum power point and is how we want to run the panels if we can. A couple of matters. First, every cell needs to be in the sun. If there are shadows on the panel, the affected cells will produce significantly less current, and since the cells are in series, a single shaded cell can pull down the output of the whole panel. So, mount the panels where they're unaffected by shadows if you can. Also, different parts of the country get different amounts of total sunshine, from nearly every day in Arizona to hardly any at all in some parts of upstate New York. There are maps available that can give you rough guidance, and data is available for the entire Earth. Now, the sun moves across the sky. Shouldn't the panels always be pointed at the sun? Well, yes, and there are systems to do just that. But these systems are cumbersome and expensive. These days, it's actually less expensive to simply use the money that you would have used on the tracking mechanism to simply add a few more panels. Panels really are getting less expensive. When I wrote the article 21 years ago, panels cost around $5 per rated watt. Now they're around $1 per rated watt, so a 200 watt panel can be had for in the neighborhood of $200. While it is true that solar panels have no wear-out mechanism and thus will work for many, many decades, in order to reduce cost, the panels have gotten flimsier. Note that my 250 watt panel is rather bendable, which is not good for it, so however you mount them, make sure you're not counting on the panel itself for structural stability, but rather the mounting system needs to be strong enough itself. Now, just one more thing on panels. Originally, they were all made to support 12-volt systems. All my panels that are wall-mounted here are 12-volt panels, and the one on the left is the original Arco panel. All these panels are wired in parallel. Each contributes what current it can. But newer panels are made for 24-volt or even 48-volt systems. My newest panel is actually a 24-volt panel. Can that work with a 12-volt ham system? The answer is a qualified yes, as I'll explain later. Sitting silently in the background is the backbone of my photovoltaic system, the battery. The battery stores all that energy in chemical fashion and is prepared in an instant to deliver it up to the load. Now, there are lots of types of batteries, and more progress has been made on batteries in the last 5 years than in the prior 50. But still, the best storage battery for a photovoltaic installation remains the lead-acid battery. These batteries are ubiquitous. After all, there's one in every automobile and truck. Yes, it is true that lead is heavy. If your need is for lightweight portability, you'll go to lithium-ion, but these take very special handling and the charging procedures are onerous. So, lead-acid. There are several types of lead-acid batteries. The normal automobile battery is designed to deliver a whole bunch of current at once to start your car, but is not designed for smaller load for a longer period of time. The marine battery, often sold in places like Walmart, is not a true deep cycle battery, but will do for smaller solar installations and can run your 100 watt HF rig for many hours. The real deep cycle batteries designed for photovoltaic systems have thick lead plates and are designed to be discharged deeply without drastically shortening the battery's life. Now, there are many types of deep cycle batteries. They are the flooded lead acid that have to be checked every so often for electrolyte levels and periodically equalized. And I really don't recommend these because of the perpetual acid haze and how sulfuric acid eats through my clothes. I used to have some of these, and it was a happy day when I got rid of them. I use a type of sealed battery that's called AGM, or absorbed glass mat, a way of keeping the electrolyte where it needs to be. Technically, AGM batteries can be mounted anywhere, including upside down. So, here are some batteries I use. My main storage location near the solar panels are these 6-volt behemoths wired in series parallel for 12 volts and can store 440 amp hours. True deep cycle batteries work best if never allowed to discharge below 50% charge. Mine are over 10 years old and, knock on wood, are still going strong. Now, I also have an inexpensive Walmart so-called deep cycle battery, the kind used for the electric motor on a bass boat. This is right next to my rig and is charged by the main battery. Also, here's an example of an 8 amp hour battery that I use for QRP and for experiments. Okay, a little about lead acid batteries. The charging voltage can go as high as 14.4 volts DC, so be sure your radio can handle a voltage that high, which it will see during the day. This chart shows the rather wide voltage excursion seen by solar-connected equipment during peak sunlight. When a fully charged lead-acid battery is rested, meaning it hasn't been charged or discharged for several hours, its voltage is about 12.7 volts when full. A 50% discharged lead-acid battery will, once rested, give you 12.0 volts. Quite simply, don't operate your batteries below this level of charge. Can you ruin a lead-acid battery? Yes, if you're determined to do so. If you allow an automobile battery to discharge below about 50 to 75%, it may well cease to hold a charge. These batteries are rated not by amp hours, but by cold cranking amps, meaning lots of current at once to start your car. Even true deep cycle batteries don't like to be discharged below 50%. You'll get the best life out of them if you discharge them lightly. Now, if you allow the charging voltage of a sealed lead-acid battery to go above 14.1 volts, gaseous hydrogen starts to build up. These batteries have a safety vent so they don't explode, but once they've been vented, they tend to dry up. So, limit that charge. Another way to ruin or damage a battery is to charge or discharge it too fast. If C is the amp hour capacity, say 100 amp hours, then a good drawdown rate is an average of C, the capacity, divided by 5 to 10, or 10 to 20 amps in this case. When charging, avoid pushing current in faster than that same rate. In passing, I note that the trickle charge voltage for lead-acid batteries is 13.3 volts. If you have a 13.8 volt station power supply, that's a bit high. And on the other hand, 13.8 volts will not fully charge the battery either. Okay, so what else is required in your photovoltaic system? Let's look at this diagram from my 1996 article. We see that there's a charge controller between the panels and the battery. This allows the panels to properly charge the batteries, but not too much. The best solar charge controllers have a so-called three-stage charger, which covers the standard bulk charge, absorption, and trickle charging. The latest controllers do this. I have two separate charge controllers. One of them handles the 12-volt panels. The other handles the single 24-volt panel. This maximum power point charge controller is pretty sophisticated and has a built-in sensor to see if I have a 24-volt battery or a 12-volt battery. It senses my 12-volt system and has an internal DC to DC converter that converts 24 volts down to 12. Further, it's designed to allow the panel to run at its maximum power point, which is usually over 30 volts for the 24-volt panel. I like this controller. And look, the panel side of the controller might work at 30 volts at 7 amps, but then on the other side you see 14 volts at 14 amps. I picked up this controller for $120 at Atlasta Solar in Grand Junction, and similar controllers are available on the web. Note that because it contains a DC to DC converter, it might create enough radio hash to raise the noise level for your receiver. I'm fortunate that this one does not. Remember that at these low voltages, you'll need thicker wires than you might ordinarily think. Also, if you do use a 24-volt panel, note that the open circuit voltage can go up over 30 volts. 30 volts DC is generally considered to be the limiting voltage for safe contact with the human body, so beware. Also, and this is extremely important, you need to put fuses everywhere. Even the battery should have one of these giant T-style fuses, and you need to make sure no metal falls on the batteries. The instantaneous discharge rate of a shorted battery is high, and a dropped wrench can turn to splashing molten metal in a heartbeat. Regarding inverters, Note that they also contain rapidly switching elements and can create RF hash. I did have to set aside one inverter because of this. Now, there are three types of inverters. The first and cheapest is the modified sine wave, which purports to approximate a sine wave. It does nothing of the sort. Rather, it outputs harmonic-rich pulses. This works for resistive loads, but if your loads include something more delicate, these are not for you. Next up the ladder are the sine wave inverters, which actually do produce a much better approximation of a sine wave. This works for many loads, such as compact fluorescent and LEDs, as well as your computer and monitor. Then, and these cost quite a bit more, are the real workhorses and produce a sine wave and also can handle inductive loads with power factors significantly less than 1. You can use this type for drills and electric saws and motors. My inverter is the type in the middle. It produces a sine wave and is good for light bulbs. Okay, we have panels, we have the batteries, the charge controller, and an inverter for use. We've talked about everything except your radio. Mobile rigs are designed with an automobile in mind and can handle the wide range of voltages seen in a vehicle's electrical system. However, the HF rigs designed for desk use want to see 13.8 volts. My old Ten-Tech Jupiter was entirely okay with my photovoltaic system, but my new and fussier Yaesu FTDX 3000 is not. When trying to operate at night, when the battery voltage was around 12.4 volts or so, it would behave unpredictably and lock up. This problem had to be solved. So, I used a commercially available voltage booster designed specifically for this use case. MFJ makes one, the MFJ 4416C. However, mine is a TG Electronics booster and boosts the 12 volts to 13.8 very nicely and has been completely trouble-free since it arrived. You'll want to install some monitoring devices such as battery voltage, charge current, discharge current, and so on. The person who's really delved into this is Scott Dennis, AL7EM. He credits me for the idea of powering his station with solar power, but he's gone much further into it than I have, as you can see from these pictures. His system tracks the sun, and he monitors voltage and current 24/7 using devices he's created and programmed. He says it's turned into a hobby within a hobby. Good job, Scott. Now that I've painted this admittedly glorious and sun-drenched picture of Arcadian bliss, let me point out that things can go wrong. As I mentioned, shading the panels cuts their output considerably. Well, trees grow, and what was once a sunny spot may no longer be. Also, as the seasons change, trees and buildings cast longer shadows. Also, there's the weather. Here in southwestern Colorado, January and February can be pretty gloomy. This year, we had 3 weeks straight without sunshine, and the poor system suffered. I used it quite a bit, but finally decided to opt for a standard old plug-in power supply until the solar system could recharge itself, which it did pretty quickly once the sun came out again. Also, beware of the outdoor environment. Steel rusts, as shown in this little connector, wood cracks, paint peels, wires get sun-bleached, and insulation can crack. And although these panels up here were mounted so the snow would slide off, this temporarily mounted 24-volt panel is right on the ground, and snow just piles up at the bottom. I have to push it off gently with a broom so the bottom cells aren't covered. Otherwise, the entire panel won't work. And on winter mornings, this spot is shaded. It's time to remount it. I mentioned safety before. Let me mention it again. Fuse everything. Assume the worst case in which wires might be shorted. Protect your batteries and charge controllers from gallivanting children and clueless adults who might like to push buttons just to see what happens. And have a way to disconnect everything very quickly in case you need to. I have a single disconnect switch here to shut everything down and disconnect the panels, batteries, and load from each other. Train others in the household how to use it. You may wish to contact a solar qualified electrician to install your system. And if you want to experiment with feeding energy back to the utility company, you most certainly must let a qualified electrical technician do the job. Well, there you have it. I've gone well past the simple system I wrote about 21 years ago. While it's more complex than before, it follows the same basic principles. And you're an amateur radio operator, so go experiment. Please click like, please subscribe, and click on the bell. Don't let the bed bugs bite. Check out my website and tip jar. Until next time, 73.